I am going to start a video lecture about this. First one, I consider D over theorem, then root of a complex number with the help of D over theorem. Then we have some examples, or in this application of D over theorem. So D over theorem states that when n is a integer, positive and negative, n is an integer, positive and negative, then cos theta plus I sin theta whole to the power m equal to cos n theta plus I sin n theta. This is for reversal for positive integer and negative integer. Now when we consider n is a fraction, positive or negative, then cos n theta plus I sin n theta is one of the values of cos theta plus I sin theta whole to the power n. This is one of the values. So this is the statement of the de Moivre's theorem. Now applying this de Moivre's theorem, you can find the roots of a complex number. Suppose we consider a complex number z is equal to x plus iy. We need to find the roots of a complex number. Say nth root. So what is the nth root of z? To find the roots of a complex number, we need to express z in polar form. First, step 1. Polar form, that is, say z is the polar form of z is where r is and theta lies between. Theta is the principal argument, r is the modulus of z. Now once you express this in polar form, now we start to find the roots of the complex number z, nth roots. Now we know that cos of theta same as cos twice n pi plus theta. Sin of theta same as sin twice n pi plus theta. So for nth root means we have n values of z. Nth root means we have n values. Now for those values, n values, we have to consider in this way. So z is equal to r cos theta plus I sin theta. Now we put, instead of theta, we put cos twice n pi plus theta plus I sin. Okay, I write k here, no problem. K is an integer. So twice k prime plus theta and twice k pi plus theta. K is an integer. Now to find the nth root of z, we need to express in this way: 1 by n and cos twice k pi plus theta plus I sin twice k pi plus theta whole to the power n. Then it can be written by using de Moivre's theorem. This can be written as r to the power 1 by n cos twice a pi plus theta by n I sin twice k pi plus theta by n. Now we have to consider nth roots and values of z to the power 1 by n. So we have n values. So what about the values of k? K is an integer. K is an integer. We have infinite values of k. Now out of infinite values of k, we consider only n values, and those are distinct. So in this way, we consider k from 0, 1 up to n minus 1. 0, 1 up to n minus 1. Now you see k takes any values of z. That means k may be minus 1, k may be n plus 1 also. But out of these infinite values of k, these are the only distinct roots of. For these values of k, we have distinct n values. And so we have the roots of z to the power n are distinct. For k equal to 0, you have cos twice pi, theta by n plus I sin theta by n, so on. For k equal to 0, you will get this, then k equal to 1, you will get another root, then k equal to n minus 1, you will get another root. So ultimately you will get nth roots of z. So by using the one method, you can find the roots of the complex number. To find the root of a complex number, first you have to express complex number to polar form, and then to find the roots in this way. Now we apply this method to find the roots of 1. I'm going to find the roots of 1. So you can express 1 cos 0 polar form of this. Now 1 can be written as 1 plus I0. So if we express 1 in polar form, you will get R is, what is R? 1, and theta will be 0, principal values of the. So now we have 1. Find the roots means I think we call it cube root. Okay, cube root. So this is same as twice k pi plus 0 I sin twice k pi plus 0. You can write it this way when k is an integer. So we take k infinite values of k. Now out of this we consider only 3 values. So 1 cube root of 3, 1, then it will be cos twice k pi plus I sin twice k pi 1/3, and this is where k is 0, 1, 2, 3 values, because we consider cube roots. So cos twice k pi by 3 plus I sin twice k pi by 3, k equal to 0, 1, 2. So in this way you will get 3 values of 3 roots of 1. That is the cube roots of unity. Now we apply this universal here to find the roots of cube roots of unity. So you take any complex number and you find the roots of the complex number, whatever it may be, maybe 6 root, maybe 6 root, etc. Now with the help of again roots of complex number, you can solve this type of problem also. How can you find the solve? It has 6 roots, because 6-degree equation we have 6 roots. So to find the 6 roots, now you cannot apply directly to this equation. You cannot apply directly to this equation to find the roots. You cannot apply the universal directly. So you can express x 5 x to the power 4 x cube squared x plus 1, it is nothing but x to the power 7 minus 1 by x minus, you know this. So to find the roots of this means find the roots of this. So if we consider this equal to 0, that means we have to find this equal to 0. So what is the, if we put this equal to 0 first, then we have x equal to 1 to the power 1 by 7. Like cube roots of unity, you have to determine 7 roots of this. Cos y k pi by 7 plus I sin y k pi by 7, where k equal to 0, 1, 2, 3, 4, 5, 6. So you have 7 roots of 1 in this way. Now, when we put k equal to 0, then it will be 1. Putting k equal to 0, we have x equal to 1. Then putting k equal to 1, k equal to 2, so on, k equal to 6, you will get say x equal to alpha square, so on. Say, then out of 7 roots, we have, this is 6 roots. So, and the roots of this equation is, so the roots of x6, x5, x plus 1 equal to 0 are same as roots of x to the power 7 minus 1 by equal to 0. Same. So, out of these 7 roots, one is here x minus 1 equal to 0. This is one of the roots. So, you can express x to the power 6. So, except 1, you have different roots. Thus, the roots of x to the power 6, x plus 1 equal to 0 are alpha, we call alpha square, say alpha square, so on, say alpha 6 plus 1. These are the roots of the equation, because this is nowhere here, because we consider x to the power 7 minus 1 equal to 0. We find the roots of 7 roots of 1. Now 7 roots of 1, if we if omit 1 roots when k equal to 0, this root is not there. Except this, all these are the roots of the x to the power 6. But again, in this way you can find the roots of this such type of equation. There are so many such type of equation you can find in this way. You can express this equation in another way. If we express this, then you can apply for d over square. Otherwise not. Then last one, we call it, say example, it is a theoretical part. Expansion of cos theta plus sin theta. Now you know that d over square tells when tan is an integer, positive, negative. This is to the power n equal to cos n theta plus I sin n theta. We know that. For positive integer or negative integer. Now here it is given n is a positive integer. So d over 7 can apply. Now you can expand left hand side binomially. What happens? Expand left hand side binomially. Then you will get, what will be the first term? N C1 cos to the power n theta plus, I sin n theta to the power 0 actually. Then NC2 cos n minus 1 theta I sin theta to the power 1. Is it okay? Huh?
So, NC0 so NC0.
Okay. NC0, NC1. Okay. Then NC2 cos to the power n minus 1 theta 2 I sin theta to the power square, so on. And lastly NCn cos to the power 0 n minus n actually theta into I sin n I sin theta to the power n. So this is the expansion of left hand side of this figure. Now you collect the term free from I and with I left hand side. Then you will get this will be the term with I and this is without I. So it is NC0 cos to the power n theta plus this will be the term free from I. So NC2 is negative. NC2 cos to the power n minus 2 theta sin square theta plus and finally we have with I. This is the first term. NC1 cos to the power n minus 1 theta sin theta. Then this will be the next term finally. So in this way we have only few terms. So we have some terms having no I and some terms with I, like that. This will be. So now right hand side is already a plus ib form. So equating real and imaginary part, you will get the result. Equating real and imaginary parts. From both sides. Both sides of 1. We have left hand side is given by me, then with I. Then we have cos n theta. This is the real part of the right hand side, and it will be first one. NC0 cos to the power n theta minus so on. Then sin n theta, which is the imaginary part of the left hand side. So it will be like this one. NC1 cos n minus 1 theta sin theta so on. So in this way you will get the expansion of cos n theta and sin n theta. So this is the application of the over story. We have two applications here. First of the roots of the complex number, and second one we can expand cos n theta and sin n theta in this way. So today we conclude this lecture at that point, and next class we will continue the process. Thank you.